Good afternoon, students. Today we have a lecture on CPU scheduling, which is an important chapter of the operating system subject. Okay. So first, we are going to the introduction. That is, what is the scheduling? Scheduling refers to the set of policies and mechanisms that an OS supports for determining the order of execution of the pending jobs and processes. That means many number of processes, those are executing on a CPU, and which process will execute first, that depends on some scheduling algorithm. That which process will execute first and which process will execute next. A scheduler is an operating system program that selects the next job to be admitted for the execution. That means the main purpose of the scheduler, that the scheduler is a job, or it is a program, which is an operating system program that selects the next job to be admitted for the execution. New process that is coming, new one process that is coming, and according to some priority, it is dedicated or it is assigned to the CPU for the execution. Note that the main objective of the scheduling is to increase CPU utilization, which is very important, CPU utilization, and to increase the throughput. So main thing is we have to increase the CPU utilization and increase the throughput. Now, throughput is the amount of work accomplished in a given time interval. That how much execution is faster, that is our objective, and for that we have to do scheduling, and which process will execute first, which process will execute next, that depends upon the scheduler. Also note that the behavior of a process plays a key role in CPU scheduling. That is the behavior of a process that is depicted by a CPU IO burst cycle. Means what is that? Look at this diagram. Now here you may observe there is a CPU burst, IO burst, CPU burst, IO burst. What this means? Now when a process that is executed, when it is assigned to the CPU, we call that particular thing as a CPU burst. Suppose for example the instructions load store, add store, read from file. That means right now these instructions are executed, and it is going through the CPU, and we are calling this as CPU burst. Now read from file, look at here, read from file, this means what? Now the process need to do some IO operation. So after that, wait for IO, this is the, we are calling IO burst. That means when a process that is executed, sometimes it may need for the input output. At that time, CPU or the scheduler will schedule some other process to the CPU. Okay, so the two cycles, CPU burst cycle and IO burst cycle, they are actually formed in this way. So in the previous figure, the process execution consists of a cycle of CPU execution and IO wait. So this one is just the execution of the CPU burst cycle and IO burst cycle. There are three different types of schedulers to schedule processes at various levels. Okay, that means three types of schedulers. Okay, this is not that there are various types of algorithm. According to their characteristics, there are three different types of schedulers. What are those? Long-term scheduler, medium-term scheduler, and short-term scheduler. There are three types of scheduler. So this is a normal process state diagram, 7-state diagram, where there are 7 number of states. That means these are new process, a process that comes, or new one process. It go to the ready state, then from to the ready queue, then for the running, then if it is going for IO, it may be blocked. Normal 7-state process model basis. Now, what I am trying to say that what is the position of that mid-term scheduler, short-term scheduler in this particular process state diagram? The previous diagram is exactly same, but I am just removing the arrows here in this case. Now look at here, long-term scheduler they are assigning here, long-term scheduler. Midterm scheduler are mainly assigned in this case were ready or suspend state to the ready state, blocked or suspend to block state. These are mainly dependent on mainly we call this type of scheduler as a midterm scheduler. And the short term scheduler, that means ready to running, that means in this case the processes that are assigned to the CPU, we call this as a short term scheduler. So again I am telling you that the long term scheduler, the scheduler, there are three types of schedulers: long term scheduler, short term scheduler, mid term scheduler. Three types of scheduler. So the definition of the long-term scheduler is also known as a job scheduler. Decides whether a new process can be added to the ready queue now. So this is the main. The new process is assigned to the ready states. Okay, these are the case of the long-term scheduler. What is the mid-term scheduler? Now, mid-term scheduler is a part of the swapping function. That means those processes which are currently in the ready state, okay, they may be transferred to the secondary storage. Okay, and when it is required, it again came back to the primary memory. So for this, we call this as a swapping. And for this swapping, the mid-term scheduler actually takes place. Now, if you look at this diagram again, that you will observe midterm scheduler position is here, midterm scheduler is positioned here. Okay, that means from the ready state or suspend state, ready suspend state to the ready state, or block suspend state to the block state. In this portion, we have a midterm scheduler or medium term scheduler. Third one, that is a short term scheduler. It is the, I told you earlier that this is the case of when from the ready queue it is going actually assigning to the CPU. At that time, short term scheduler takes place. The short term scheduler selects a process from ready queue. I told you from the ready queue to the running state. From ready queue among the ready processes to execute on the CPU according to the scheduling algorithm employed on that system. So this one, that is a ready to the running. In this case, short-term scheduling takes place. This is another diagram. This is another diagram where we can show you that where is the actually it is placed. That is a long-term scheduler. It is placed here. That is a new jobs or new process that are coming. Now in this diagram there are many number of queues. So when the ready queue to the processor or to the CPU, it is the case of the short-term scheduling, and ready queue to the other ready queue operations, blocked or suspended queue. These are the cases of the mid-term scheduling. So this is just showing, this diagram is just showing, so where actually the long-term scheduling, medium-term scheduling and short-term scheduling take place. Priorities. Another important topic, that is when we have a scheduler, the scheduler selects the job or the process. Okay, they have to choose the process according to their priorities. That is, scheduler will always choose a process of higher priority over one the lower priority. And that means higher priority job will get placed first, then it comes for the lower priority job. So it have a multiple ready queues to represent each level of the priority, and the lower priority may suffer starvation. That means if in a case that when there is a process which have a lower priority, and in that case what will happen, higher priority job will always execute first. Okay, and the process who have a lower priority, okay, can't allocate to the CPU for a long time, and we call that as a starvation. The terminology we are using is a starvation. Scheduling criteria. So when we are using the scheduling algorithms, there are some terminology we have to use. That is CPU utilization, throughput, turnaround time, waiting time, response time, etc. Now, in the turnaround time, we have to calculate because many number of cases we have to solve some sort of scheduling algorithms. At that time, we have to use or we have to calculate what is the turnaround time, what is the waiting time, what is the response time. So these are actually turnaround time is equal to finish time minus arrival time. Finish time means arrival time. This is arrival time of a process. Finish time of a process minus arrival time of that process. Similarly, waiting time, that is calculated using starting time of process minus arrival time of that process. Similarly, response time, it is calculated as the first response. That means first it is assigned to the CPU and minus arrival time. In this way, we have to calculate the turnaround time, waiting time, and response time of each and every process. So, same thing here, that how we are calculating this. I'm skipping this one. Now, the first scheduling algorithm we have to encounter, that is a first come first serve scheduling. That means how the priority is calculated for this type of scheduling algorithm. Now, the process which comes first will be allocated first. So the process which comes first have a higher priority. So that is allocated to the CPU first, then the next. This is an example that these are the processes. That is the P1, P2, P3, three process, and the burst time. Burst time is the CPU burst time. That how total computation time of the process P1 is 24 unit of time. P2 is 3, P3 is 3. Okay. So how we represent this particular scheduling using this a pictorial form of the representation, we call this as a Gantt chart. Now in the Gantt chart, you may observe how we are scheduling this. The process P1, normally, if suppose that the process arrive in the order P1, P2, P3, maybe we are assuming here all the process P1, P2, P3, they arrived at time 0. But for this example, we are assuming that P1, P2, P3 arrives at time 0, but let P1 comes first, then P2, then P3. Now for that, P1 will be executed first. Now this one is a non-preemptive scheduling. That means when a particular process assigned to the CPU, it can't be removed. Okay. No one process P2 or P3 can preempt this particular process. Now for this, so in this case of first come first serve, P1 will be assigned first. So 0 to 24, P1 is assigned. Then P2, 3 unit of time, P2 is assigned. Then P3 is coming, P3 is assigned. So we call this as a Gantt chart. And from this example, it is important that how we have to calculate the average waiting time, turnaround time, etc. Now, if I ask you that what is the waiting time for the process P1? P1 arrives at time 0. Okay, but so the waiting time of the P1 is 0 simply. Arrival time of P2, it is also 0, but waiting time, but it starts up from the time unit 24. So the waiting time for the P2 is P2 equal to 24 minus 0. Similarly, P3 it is equal to 27 minus 0. Why 27? The P3 arrival time is P3 is 0, but it is started from 27. So waiting time for the P3 is 27 minus 0. So average waiting time is this 0 plus 24, then 27 divided by 3. So 17 is the answer of the average waiting time. Similarly, turnaround time. What is the turnaround time? Now finish time minus arrival time. So turnaround time for P1, finish time. What is the finish time? 24. 24 minus arrival time. Arrival time is 0. Similarly for the P2, P2 finishes at 27. 27 minus 0. Similarly, for the P3, it is 30 minus 0. So, in this way, we have to calculate the turnaround time for each and every process, and average turnaround time is this 24, then 27 plus 30 by 3. That is here 27. Response time is actually the first response minus the arrival time. So first response P1, that is a 0, P2 is 24 minus 0, and P3 is 27 minus 0, because first response minus arrival time. Say for example, again P3, first response is 27 minus arrival time, that is 0. So average response time, that is calculated 70. Suppose that processes arrive in the order. Similarly, in the previous example, suppose the process arrives in order P2, P3, P1. Say P2. So P2 will be allocated first 3 unit of time, then P3 3 unit of time, then P1 rest of the unit 24 unit of time. Okay. So in that case, our Gantt chart will be look like in this way. Okay. In that case also, we are calculating the waiting time, average waiting time. So in this case, it is much better than the previous one. Another scheduling algorithm, important scheduling algorithm, that is the shortest job first scheduling. That means by the name, how the priority is calculated, the job or the process which have a minimum burst time will be allocated first to the CPU. Okay, that means the process which have a lower execution time will be or have a higher priority than the other process. So it associates with each process the length of its next CPU burst. Use this length to schedule the process with the shortest time. Now there are two schemes. In the shortest job first, there are two things. One is a preemptive, another is a non-preemptive. Preemptive means, again I am telling you, now when suppose a particular process that is executing, at that time some higher priority job that is arrived. So what will happen? The next job which have a higher priority, it will preempt the lower priority process. So, and non-preemptive means once CPU given to the process, it cannot be preempted until completes its CPU burst. So for example, in the case of the for example here, P2 it is assigned, then P3 and P1. Now here suppose P1, P3, P2, okay, all are arriving at the time 0, but P1 can't preempt P2 or P1 can't preempt P3 because this FCFS is completely a non-preemptive scheduling algorithm. But in the case of shortest job first, there are two schemes, non-preemptive and preemptive. Shortest job first is optimal. It gives minimum average waiting time for a given set of process. So this one, so we also have an example for this. So this one is the first example of the preemptive. So for first of all, there is an example of non-preemptive. Suppose these are the process. This is the arrival time. This is the burst time. So how this one or how the scheduling algorithm will take place in the case of. So arrival time is 0. That means at the 0th time, there is no other process. So first P1 will be allocated. So at the 0th time, only P1 process available. So P1 is allocated. This one is a non-preemptive. That means once P1 is allocated, no other process can preempt this P1. Then P2, it is arrived at time 2. Burst time is 4. But this is not allocated. P2 is not allocated. Why? Because P3 also arrived at time 4. At time 4, in this case, the time 4, P3 also arrived and it have a burst time 1. So right now at the 7, P4 also arrived at the time 5. So at the time unit 7, P2, P3, P4, all three processes arrived. Now among this P2, P3, P4, which have a higher priority, we will observe here first time of P2 is 4, 1 and 4. 4 is for the P4. So lowest time is for the P3. So the lowest job, that is for the P3, will have the higher priority. So we have to allocate P3 here, only 1 unit time. Then P2 and P4 are left. So we may use P2, allocate P2 here. After that, allocate P4 here. This is the case of the SJ, that is the shortest job first, which is a non-preemptive. Now, if we use the example of preemptive SJ, that means now higher priority process can preempt lower priority process. So in this case, P1 is 0, 7. Look at here. P1, it is allocated 0 to 2. 0 to 2. Now, at this time and this time, P2 arrived. So, P2 have a burst time 4. Now, what is happening here? P1 executed only 2 unit of time. So, it remains 5 unit of time. So, here it is 5 and here it is 4. That means the higher priority is P2. Now, P2 preempts P1. So, P2 will allocate it. P2 is 4 unit of time. But at the time 4, P3 arrives with a higher priority because shortest job, that is a 1. So, we have to allocate P3 here. Then again, right now, it also have a 4 unit time, but it already executed, P2 already executed 2 unit of time. So, lower higher priority is P2. P2 is allocated. After that, 4 unit of time, that is a P4 is left. P4 is allocated. After that, P1 is allocated because P1 remains is 5. 5 unit is allocated. So, this is the example of preemptive SJ. Okay. So, among these two, again I am telling you in the case of the SJF, there are two types. One is a preemptive, one is a non-preemptive, and this is the example of preemptive SJF where one process, higher priority process, can preempt lower priority process. Thank you.